right, so Chapter 1, what we've done so far is basically a review of vocabulary, and we started doing some conversions using dimensional analysis. We talked about significant figures, and we're going to do a little bit more of that today and a little bit more review of vocabulary. Okay? So I said to you, no, whoops, I don't have this connected. Just kidding. Maybe I do. Yes, I do. Okay. We did some conversions using our dimensional analysis. If you are converting temperatures, you don't need to use dimensional analysis. We will most of the time be in units of Kelvin, sometimes Celsius. We will never be in Fahrenheit. And getting back and forth is just taking a Celsius temperature and adding 273. If you had a Kelvin temperature and for some reason you needed to go back to Celsius, you would subtract 273. Okay? Alright, let's talk density. Okay, hopefully you remember the formula, mass divided by volume. And technically, if you're solving for a density, you can have mass in any unit of mass, grams, kilograms, decagrams, divided by any unit of volume you want, milliliters, liters, cubic centimeters, whatever. You will see density typically expressed in specific units. And I want to just remind you, hopefully you learned this in Chem 1, do you all remember that a milliliter and a cubic centimeter are the same volume? If you don't, I'm reminding you now. Okay? Any of you that go into any kind of medical field, anytime they give dosages of something, it's usually in units of cc's. cc stands for cubic centimeter. So when they say 20 cc's of penicillin, they're really just saying 20 milliliters. Okay? For whatever reason, these are the two most common units of density. Okay? I know they mean the same thing, but if you ever see a number that's associated with a solid, densities of solids are typically expressed in units of grams per cubic centimeter, whereas liquids and gases are typically expressed in grams per milliliter. I don't know why. It's mathematically the same, but that's just the way it is. Two vocabulary words that, the first one you may not have learned in 10th grade, the second one you probably did, but they're important vocabulary words for you to know. Okay, density is a physical property that can be described as an intrinsic property. The word intrinsic means unique to that substance. All right, if you say that a substance has a density of 3.84 grams per milliliter, there is no other substance that is going to have that exact same density. It is unique to that substance. The second word, hopefully you did learn in Chem 1, although you may not remember. Does anybody remember what an intensive property, what that means? It was at the very beginning of the year, a long time ago. Yeah. Right, it means a property independent of amount. And let me give you an example, okay? Let's take one substance. Let's take ice as an example. If I have an ice cube versus an iceberg, they are made of the same material. Are they the same size? Not even close, okay? But guys, they have the same density. Changing the amount of the material does not change the density. What is the opposite of intensive? Extensive, meaning a property that does change when you change the amount. Can anybody give me an example of an extensive physical property? An ice cube and an iceberg will have very different masses. Okay? What's another one? Volume, weight. These are all examples of extensive properties. Okay? The density is intensive. Okay, we're going to do another practice problem, and I love this problem. It is a very classic AP chemistry kind of problem. What I mean by that is, when you read through it the first time, you're probably not immediately going to know how to solve it. If you do, hey, great. Good for you. Okay, but let's just kind of look at it together, and then I'll let you try it on your own. The problem says we have a 55-gallon drum, barrel, container, whatever. Gallons, ladies and gentlemen, that's a unit of what? Volume. Okay? 55-gallon drum says it weighs 75 pounds when it is empty. What will be the total mass, and I've made the word total in bold. What will be the total mass when that barrel is filled with ethanol? Ethanol is a substance. I've given you some pieces of information that are going to help you solve this problem. The last thing I want to say before you try it on your own, your ultimate final answer is a mass. Masses are expressed in what unit? Grams. Not pounds. Okay? Pounds are weight. So you've got to find the total mass of a barrel filled with ethanol. Ladies and gentlemen, first thing, because I heard a number of people mention this. This is a multi-step problem. Okay, you don't want to round for sig figs until your final answer. Okay. question. Yes?
Does it matter if our fundamental is in grams or pounds?
Yes. Pounds is the unit of weight, not mass. Good question. Last class somebody asked, does it matter if our final answer is in scientific notation? Nope. You can put it in scientific notation if you want. I didn't, but you can. As long as it has the right number of significant figures, you're good. Other questions? Okay. So, the reason I did this problem, multiple reasons. One, it's a good multi-step problem. But also, I want you all to get used to using density in one of your earlier steps in a multi-step problem. Very, very common in AP Chem. You're trying to solve a problem and you need the mass of some material in order to finish the problem. Let's say they didn't give you the mass, they gave you the volume and the density. If you have a volume and a density of something, you can find that mass that you're looking for. And that's what we did in this problem. Or sometimes they'll give you a mass and a density, and what you really need is the volume, and you can get it. So get used to using density to solve for something that you need. That's a really common thing in AP Chem. Okay? All right, let's finish up this chapter. The end of chapter 1 is just on matter, mostly a vocabulary review. Matter, anything that occupies space and has mass, that includes gases. Many people think gases don't have mass. They do. Okay? 3 states of matter: solid, liquid, gas. Okay? Basically, I just want you to know their characteristics in terms of shape and volume. Solids, fixed volume, fixed shape. Liquids take the shape of their container but do have a definite volume. Gases have neither fixed volume nor a fixed shape. And I want to make sure you all understand this concept of not having a fixed volume, because that's sort of a strange concept. But I want you to understand that I could take all the gas in this room and compress it to a much smaller volume and have it still be in the gas phase. That is possible. Gases are very compressible. Solids and liquids are not. That's why we get that difference. Okay. Again, a vocabulary review here. When we're talking mixtures, homogeneous versus heterogeneous. First of all, this is too long for me to say, homogeneous mixture. There is a word I'm going to use instead. I am going to use the word solution. They are synonyms. So anytime you hear me use the word solution, that means a homogeneous mixture, a mixture with a uniform composition. It's the same throughout. Heterogeneous, not the same throughout. And folks, the best way to decide whether a mixture is homogeneous or heterogeneous is to ask yourself a question. If you took a sample of this mixture from one part, one place, and took a separate sample from another place, a different location, would they be molecularly identical? Let me give you an example. Let's say I took 2 blood samples from you. I took one from your foot and one from your finger. Exact same volumes. Would those blood samples be molecularly identical? Do you think? What do you think? Do you think they would have exactly the same number of red blood cells and white blood cells and platelets? Probably not. Your blood is a heterogeneous mixture. Let me give you another example. How about air? If I took a sample of air from this room and a sample of air, same volume, from out on 66, would they be molecularly identical? What do you think? Think about a sample, anytime you take an air sample near a road, particularly a big road like 66, you're going to have a lot of pollutants out there that you don't have in here. Okay. What about, think of a good example. How about, like, you make a mixture of lemonade. You take the type where, you know, it's the powder and you dissolve it and you stir it up, and you haven't added so much that it's piled up at the bottom. It's all dissolved. Is a pitcher of lemonade homogeneous or heterogeneous? Homogeneous. Okay. One little clue for this one, the first homogeneous. Anytime something says something dissolves in something else, if you see the word dissolves, that is automatically homogeneous. That's a little clue. Okay. Now, if we're still talking mixtures, both homogeneous and heterogeneous can be separated using physical separation techniques. There are more than 4. These are the 4 I want to focus on, and I'm going to talk very briefly about each one. I'm actually going to start at the bottom here. Fractional crystallization is a very fancy term for a very simple process. If I give you a sample of salt water, and I say I want the crystalline salt back, how are you going to do that? Evaporate the water. Boil it off. Evaporate it off. Either one. And what we'll be left with is the crystalline solute. Fractional crystallization just means boiling off the solvent. That's all that means. To be left with a crystal. Distillation is a method you would use to separate 2 or more liquids from each other if you had a mixture of liquids. And I used to do this demo, and I broke the glassware for it, so I can't do the demo anymore. But what I used to do was take a sample of cherry Coke, put it in a flask, put a Bunsen burner under it, and within about 30 seconds it started to boil. You could very vigorously see, it was boiling. And I had this apparatus that all of the vapors that were coming off of this cherry Coke as it's boiling would go up this glass tube, down another glass tube, and those gases would condense back into the liquid form, and I collected the liquid in this little beaker. And when we did this demo, this clear liquid would end up in the beaker, and I would say, what is this? And just at first glance, everybody would say, it's water. All you did was collect the water vapor, condense it, there's the water. It wasn't water. And to prove it, I did something that you should never do in a chem lab, which is I made people not waft this clear liquid. No, I made them like stick their nose right in the beaker and take a big whiff. It wasn't water, it was cherry extract, which is clear. It looks like water, doesn't smell like water. What ended up happening is the cherry extract boils at a lower temperature than water. So all that cherry extract boiled off first before the water boiled. That's a way to separate liquids based on their different boiling points. Okay? So when you buy distilled water, all that means is they've taken samples of natural water, boiled the water, condensed it, and removed anything that anything that has a different boiling temperature than water. Any other liquid that could have been contaminated. Filtration is your simplest one. Take a sample of creek water. It's got rocks, it's got dirt, it's got sticks in it. You pour it through a filter, the water and the small, fine particles are going to go through the filter. The rocks and the sticks and the bigger particles are going to catch on the filter. Filtration is separating things based on what property? Particle size. The smallest particles will run through. The big particles will get stuck on the filter paper. And then this first one, which really has limited use, chromatography, is used to separate dyes, inks, dyes that are found in nature. Many of you probably did a lab in your Chem 1 where you took black ink and separated it. Black ink really isn't just black ink. It's red ink, blue ink, green ink, yellow, pink, all put together. And this allowed us to separate that black ink into different colors. And that's about as much detail as I want to go in about it. Okay. So, if something is not a mixture, it must be a pure substance. Elements are your simplest. Compounds are a chemical, let me stress that word, a chemical combination of elements. What would you call a physical combination of elements? You wouldn't call it a compound, what would you call it? A mixture. Yeah. A compound is a chemical combination of elements. A mixture is a physical combination. And that is it for chapter 2. Alright, ladies and gentlemen, this is an exciting day. I am giving you your AP periodic table. I know, get excited. Ladies and gentlemen, I want to call your attention. Some of you probably have already noticed some differences between this periodic table and the one you had in your sophomore chemistry. First thing I want you to notice, there are no names on this periodic table. Not to panic, not to panic, okay? Test questions are not going to ask you some random element that, like number 107. I don't even know what that is, okay? They're not going to ask you those. They are typically going to ask you elements pretty much in the first 4 rows. Now you may not know every single one in that group, but you probably know most of them. Now does that mean they could ask you an element outside of that area? Yes. But, folks, we're talking ones that I promise most of you know. Like, what's element number 47? Silver. How about the one just below it, 79? Gold. How about number 80? Mercury. 82? Lead. How about the one above it, number 50? Tin. This one maybe less people know. How about number 74? Don't say water.
Oh, it's tungsten, yeah, it's tungsten.
It's tungsten. How about this one? What about number 55? Cesium. Okay, now let me tell you this. Are they ever going to ask you some of these really random ones? Probably not, but if they do, they will tell you the element name and symbol, usually and atomic number, so you can find it. Okay? Please don't worry about memorizing the periodic table. Okay? All right. Now, again, guys, I'm going to just buzz through the beginning part of this chapter because that's really not where I want to focus. It's not that it's not important, it's just less important. Alright? So what starts off in chapter 2 is a lot of the history Okay, the first scientist that we see, the one that is really the first in modern chemistry, is Antoine Lavoisier. Okay, he is responsible for a number of laws, the first one being conservation of mass. Mass cannot be created or destroyed, it can just change forms. Okay. This law of definite proportions is, when I explain it to you, it's something that is so commonplace to us that you're going to say, well, duh. But I guess back in the 1700s, this was kind of revolutionary. I want to give you an example. Simplest one. Water. If I take a sample of water from Oakton, and I take a sample of water from Madagascar, it doesn't matter where I get it. Water is water is water is water. Water is H2O no matter where it comes from. Okay? It is always 2 hydrogens to 1 oxygen. And I know what you're thinking. Duh. Okay, well, it's the 1700s, people. Right? It just means one compound is always the same elements in always the same ratios. This one is a little harder to explain. Where I want you to focus is this second bullet right here. Okay? The law of multiple proportions basically just means you can make different compounds. These are different compounds using the same elements in different ratios. Okay? We all know this is water. Does anybody know what this compound is? Yeah. Hydrogen peroxide. You skin your knee. You put it on there. It's a cleansing agent or sterilizer. Do you agree that these are very different compounds? Yes. This one is very good for you. This, if you drink it, will kill you. Okay? They are made up of the same elements, but you change the ratio and you change the compound big time. The second example, and I'll admit I can't remember which one is which. One of them is laughing gas, which is fairly harmless, and the other one is lethal, and I can't remember which one is which. Sorry. Alright. I'm not even going to read these 4 things here. Dalton is your first guy. We're into the 1800s. Dalton is the first scientist to talk about atoms as a distinct thing. Avogadro comes on the scene a little bit later. Everything that is on this slide can be really summed up with one number. Now listen carefully to what I ask you here. Don't answer immediately. Tell me, what is the volume of 1 mole of any gas? 22.4. I heard a couple of people say 6.02 times 10 to the 23rd. That's not a volume. That's a number of particles in 1 mole. Okay? And folks, Avogadro is responsible for saying if you have the same number of particles of any gas, they will have the same volume. And I have this box, which a lot of the other chemistry teachers also have. That box has an exact volume of 22.4 liters. It might not look like it, but it does. That is 1 mole of air. Right there. Okay? I know. Wow. Exciting stuff. Okay. What's on this slide and the next slide are probably the 2 most important when we're talking history. Right? J.J. Thomson comes on the scene a little bit later in the 1800s. Performed an experiment with a cathode ray tube. Okay. And what he did, I just want to make sure you remember, he is first of all credited with discovering the electron. He passed a beam of light, a beam of electricity through this glass tube, and he put on top and bottom charged magnets. The positively charged one was on top, the negatively charged one was on the bottom. And what he observed was that this beam of light did not go straight through. It was attracted to the positive plate. What does that mean about what's in the beam?
Negative.
That whatever's in that beam must be negatively charged. And as it turns out, this was just a beam of electrons. All right, last little bit of history here. This guy, very important. Even later in the 1800s, Ernest Rutherford. Tell me the name of this experiment. You probably learned it all the way back in elementary school.
Gold foil.
Gold foil. Okay. This is a picture out of your textbook. Let me just refresh your memory of what is going on here. First of all, Rutherford is credited with discovering the nucleus of an atom. You have a beam of alpha particles being shot. What you need to know about that is alpha particles are positively charged particles. That's what's important about that. You're firing positively charged particles at a sheet of gold foil. And folks, we get two conclusions out of this. Most of the alpha particles pass straight through. What is the first conclusion? What does that tell me about an atom? Yes, Bridget? Correct. Atoms are made up of mostly empty space. What does that mean about the size of the nucleus? It's really small. Okay? Some of these alpha particles, however, bounced straight back. What are these alpha particles hitting? Other positive particles. Okay, be more specific. Positive gold particles. Protons! Thank you! The protons in the gold atoms. How come it repelled like that? Why didn't these alpha particles just stick to it? Opposites attract, like charges repel. Alright? So folks, we get two conclusions. The nucleus is super duper small, and it's positively charged. And tell me one more time, what in the nucleus is making it positively charged? Thank you very much. Okay. Ladies and gentlemen, you do not need to know these dimensions, okay? However, I want to give you an analogy so that you can sort of get a mental picture of the dimensions of an atom. I've heard an analogy said that if a person is holding a basketball in the center of Washington, D.C., and that basketball represents the nucleus, the outer edge of an atom would be basically in about Japan. Okay? Just process that for a minute.
I would say like that.
Okay? Folks, do not memorize these numbers. Do not memorize them. Okay? I assume that you all remember the various charges of your subatomic particles. The only thing I want to show you here with these masses is that your proton and neutron are the same size, and your electron is much smaller. This may not look like that big of a difference to you. That is a huge difference, okay, in size. All right. A little refresher on this kind of notation. You've got an element symbol and you have two numbers next to it. The bottom number is your atomic number. What does that mean? The number of what?
Protons.
Protons. Okay? The big number in each box on your periodic table. What is the top number? Mass number, which is the number of what? Protons and neutrons. Okay? And actually, before I talk about this, just looking at this, you should be able to then tell me how many neutrons this element has. 20. 39 minus 19 is 20. If this is a neutral particle, the number of protons and number of electrons will be equal. But what if they're not? Alright, it's an ion. I'm making it an ion. What does a charge of +1 mean? What has happened? You've lost one electron. So how many electrons does this particle have? 18. What if I did this? Which doesn't exist, by the way, but just go with me on it. Then it would be 16 electrons. What if I did this? 21. Negative charges means you gained electrons. Okay. Let's get into bonding, because I really want to get into like writing formulas, naming things, that kind of thing. Okay. We've got two types of bonds. Covalent. What's the other type?
Ionic.
Good. If you have a covalently bonded compound, shush, you can call it a molecule. Please tell me what type of elements make a covalent compound? 2 or more nonmetals, okay? Covalent means we're sharing electrons. Ionic means we're transferring electrons. See if you remember this from Chem 1. If a covalent compound can be called a molecule, an ionic compound can be called a salt. Salt means an ionic compound. What type of elements make up ionic compounds? Metal, non-metal. Alright, blah, 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 blah. Alright, we will not get into drawing structural formulas for a little while, okay? So, just pause on that. Alright, a little bit of review of vocabulary. Cation means positively charged ion, anion means a negatively charged ion. And, folks, do you remember those polyatomic ions? Oh, they are back. Your periodic table that I gave you is yours to keep. You may draw all over it, label it, do whatever you want. If you want to color code it, go for it. Okay? The only thing I would caution you about using your old periodic tables, which it's fine for you to do that, but I caution you about getting too comfortable using your old periodic table, because this is the one that you're going to have on tests, and it is not labeled. Okay? You will not be able to use your own one of these. Okay? You'll be using one of mine, which is blank, just like this one. So I don't want you to get too comfortable with that. Try to get used to using this one as best you can. Alright? So if you wish, you may label your periodic table. You are still responsible for knowing these 4 family names, group names, whatever you want to call them. Okay? Groups, families, we're talking about vertical columns, periods are horizontal. This is in general where your metals are, and there is one mistake on this slide. Anybody want to guess what it is? There is a box that is colored that should not be colored.
Hydrogen.
Correct. Okay. Do you all agree that hydrogen is in group 1?
Yes.
Yes. What's the name of group 1?
complement metal.
Correct. Is hydrogen a metal?
No.
No, it is not. It is in group 1, but it is not a metal. That is my mistake. That should not be colored yellow. Okay? I apologize. You need to know some characteristics. Metals are excellent conductors both of electricity and heat. That is why you do not want to put a paper clip into an electrical socket. Metals tend to lose electrons, not gain them. What does it mean to be malleable? What does this mean? Bendable. What does it mean to be ductile? Not duct tape, no. Stretch it out into wires. Do you know what the most ductile metal is?
Copper.
You'd think it was copper because that is what's used in wiring. It's not actually the most ductile metal. Gold. Gold is the most ductile metal, but gold is expensive, so we don't have gold wiring. It would be awesome. Alright, this is where your nonmetals are located. What's the mistake that I've made on this slide?
No.
I didn't color hydrogen in, which I should have. Okay? Because hydrogen is a nonmetal. What does it mean for something to be brittle? It breaks apart, yeah. If you drop it on the floor, it's going to shatter. Nonmetals gain electrons, and they form covalent bonds. Your semimetals are metalloids. I actually want you to look at the periodic table on the wall. The orange staircase. Any element touching that staircase is considered a metalloid with one exception.
It's aluminum.
Aluminum is touching the staircase, but folks, aluminum is definitely a metal. Think about aluminum foil. That is definitely metallic. Right? But everything else, metalloids, and characteristic-wise, folks, as far as I want you to know is I want you to know that metalloids are metal-ish. Okay? That's a technical term, by the way. Alright, here we go. Are you ready? This is the main event. Here we are. Alright. Let me first start off talking about ionic compounds. Then we'll talk covalent. Okay, remember when you are naming ionic compounds, first of all, the metal always comes first. Always. And you don't ever change the ending of the metal either. It's the non-metal, the second word, that gets that changed ending, that "-ide" ending. Okay? And the only nice thing about polyatomics, and I do mean the only nice thing, is that you don't ever have to change their names. Whether it's a cation or anion, whatever is written on that polyatomic chart is what it is. Don't change the ending. This is typically not that difficult for people. What is difficult, however, is when we get into this situation. Okay, now before I give us an example here, I want you to look again at your periodic table that I just gave you.
They don't have charges either.
Huh? Names are missing, and there are no charges either. Stop freaking out. Stop it. Just stop it. You don't need them. You think you need them, but you don't. Please tell me, what is the charge of everything in group 1?
1.
Plus 1. Group 2.
Plus 2.
Okay, we'll come back to this in a minute. How about boron's group? Plus 3, you're not going to deal with much in the carbon group. How about nitrogen's group? Minus 3, oxygen. Fluorine. Okay, there you go. Now, I know what you're thinking. Okay, that's all fine and good, but what about those transition metals? And there are metals underneath that staircase that carry multiple charges. And how are you supposed to know? You can figure it out, people. Let me walk you through the thought process. Okay? I give you this compound and I say, name it. Alright? First thing I would do is look at the metal and see where it is on your periodic table. Lead is under the staircase. That means that is a metal that can carry multiple charges. Well, how are you supposed to know what charge it is? You can figure it out. Watch. Look to the non-metal. Chlorine is a halogen. Halogens always carry what charge? -1. Okay, great. And there are 2 of them. So the entire negative half of this compound has an overall charge of -2. What does lead have to be to balance that out?
+2.
+2. Alright? So, the name of the compound would then be lead, Roman numeral 2, chloride. Let me give you a slightly more challenging one.
Uh-oh.
Let's go with this one. There, that's better. Does iron need a Roman numeral?
Yes.
Yes. Okay. You don't know what its charge is. You look to the non-metal. What is oxygen's charge? So what does iron have to be? Very good. This would be iron 2 oxide. Let me think of one. How about this? Wait a second. It doesn't need a Roman numeral. It's in group 2. Things in group 1, group 2, group 13, they don't need Roman numerals. Okay. Let's do one more. First of all, what element by name is that?
Chromium.
Chromium. Okay. It's a transition metal. It needs a Roman numeral. What do you think? Be careful with this one. You look again to the non-metal. You guys told me earlier, oxygen is always -2. You're right. What's -2 times 3? -6. That does not mean chromium has a +6 charge. There are 2 of them. Each chromium has a charge of what? What's +6 divided by 2? Okay. Chromium 3 oxide. Alright. Folks, this is the easier system. If you have a covalent compound, this is where you're using those prefixes: mono, di, tri, tetra, pent. What's the prefix for 6? Hex. 7? Hept. 8? Oct. 9? Non. 10? Dec. And we're not going to go beyond dodeca, blah, blah, blah. Alright?
We do so.
And folks, this is super duper easy. There's no charges, there's no swapping and dropping, there's no polyatomic ions. It is simply use the prefixes for how many elements there are. There's one little hitch to this. Alright? Tell me what this would be called. Nitrogen pentafluoride. How come you didn't say mononitrogen?
Think the first one doesn't read it.
You know, that's
Only use
ridiculous.
mono. Because that was weird.
You have the notes, circle that one. That is an important exception.
Yeah, also.
Okay? What about this? And I'm just making these up. These are probably compounds that don't exist.
That's awesome. Let's make them.
That.
Monochloride.
Triphosphorus monochloride.
That's kind of
The only time you use mono is if it's for the second element.
Yep.
Alright. Ladies and gentlemen, this is what I would like for you to do. I want you to name these.
Here we go.
Listen, before you get started, listen. I would suggest that before you just start naming them, you might want to decide whether each one is ionic or covalent first, because they each have their own naming system. Okay? You're going to need your polyatomics, you're going to need your periodic table. Go get them.